Hi, everyone. So I'm going to give a quick preview of the Types 2 session coming up directly after this this break. So this is a session all about types. And in programming language theory, we like to look at various ways of analyzing programs and deciding, is this a good program? Is this a bad program? What kind of behaviors can we expect from this program? And types are just a really, really successful form of static analysis, right? Where we can analyze what a program, what the syntax of a program is, and decide what behaviors it's going to have. In particular, that in a type-safe language, it doesn't segfault, right? We can now analyze that statically using types, and they're so successful because they're compositional. Right? That from one piece, when we know that this n here has type int, then we know the various functions that n can be passed to, and then it allows us to sort of do local reasoning and then to derive global properties. This is the power of types. So programmers are hungry for more types. So there's some languages that are typed. Then there are some that, well, you could say are untyped. But I think a better thing is to say unityped, right? So if you have a language like Python, you could just say everything in Python has one type. But it turns out that when people start programming in languages with fewer types, they end up wanting more of them. And so there's various different research agendas in a bunch of different languages to add more types to the language, or to add finer distinctions among types. So in all of these cases, and there's more. These were just sort of the ones that popped into my head last night. Actually, as I'm standing here, I know Python is doing the same. That should be up here. And so the papers in this session sort of are all addressing this hunger. One challenge with working with types is that type checking is necessarily conservative, right? We can't analyze a full program. Any static analysis is going to be conservative, because if it weren't conservative, it wouldn't really be static, would it? It would mean sort of running the program and observing its behavior. So instead, a type checker is going to reject some programs that still would be fine at runtime, and because of that, we often want to enhance type systems with more power, so that we can sort of carve away at this piece of the program space where you have programs that work well, yet the type checker rejects. And so that's kind of where the interesting part is in type systems research. So the 4 papers in this session, and I'll go through each one very briefly. They all introduce new ways of either eliminating bad programs or accepting good ones. So what do I mean by that? So the first paper is quotient Haskell. The idea here is that it takes a notion of refinement types and sort of flips it. So those of you who are familiar with refinement types, this is a way of taking a type such as int and making it smaller. So instead of just saying that we have the type int, we could say, well, it's the type int, but all ints that are greater than or equal to 0. And so we can say that that's the type of natural numbers, and that's a refinement on the int type. Quotient types are kind of the opposite of that, in that we're now saying instead of a restriction on the types, it's a restriction on the functions that process those types. So one example that's explored in the paper is that a bag is just kind of like a list, but it ignores the order of elements. And so what that means is that any function on a bag needs to not care about the ordering. So if your function on a bag sums all of the list, sums every element in the list using just normal addition, that's fine. That doesn't care about the order of elements. But if it does some other operation, like prints all of the elements in the list, well, that does care about the order of operations, and so that wouldn't be allowed on a bag. So this paper introduces a syntax and an implementation that allows you to make types that are quotiented, that sort of ignore some part of the encoding, and then automatically checks that restriction is preserved by functions. The next paper in the session is focusing on refinement typing. So this is another paper that relates to refinement types, these types type annotations that make types smaller. So this paper, it sort of recasts refinement typing and sort of sets things up on a more solid theoretical basis, and using the idea of focusing or focalizing. I'm actually, one question I have in this talk is exactly what the difference between those terms is. But by sort of looking at a bidirectional typing model where sometimes we're inferring types, sometimes we are synthesizing types, and then using that to sort of understand refinement typing better. The next paper in the session is about reachability typing. This is a notion of when you have a variable, what other variables can that first one access? So if I say that X equals a list containing Y, then from X I can reach Y, but at least with that definition I've said, Y can't reach back to X. And so once we start tracking these dependencies among variables, it allows us to look at, say, the memory used by a running program and perhaps partition it and say, oh, this set of variables here can't interact with those set of variables there. Because we can look at we can look at the data that each variable can reach and say that these things are separate. So once you have that, it allows you to increase your reasoning properties about the language and say that, oh, if these two variables can't access any data in common, for example, it might be safe to parallelize operations on them. Just as one example. And so this paper explores how we can track these dependencies among variables in the type system. And then the last paper in the session is actually quite similar to that one right before it, capturing types. This allows tracking of variable capture in function closures. So normally when you make a closure in a program, you can have some local anonymous function that captures variables from the context. And those variables become some kind of hidden state that's captured in that function. The techniques in this paper allow us to track that, track those captures, so that we can then figure out what effects might be performed by running that function. And this introduces a new way of sort of tracking effects and being polymorphic over effects that a function might operate on. Anyway, I'm looking forward to the session coming right up. Thanks very much for coming.